Okay, well, the good news that we now have all the tools that are necessary to solve equations. That's what we gathered here for, to solve equations. We haven't solved a single equation yet, right? We haven't done many equations. But now we have all the tools that we need to solve equations. So we, from now till the end of the semester, we will be solving equations, different types of equations. Now, what I assume that you know one form of an equation. You know linear equations. I'm just going to do a few examples just to refresh your memory of linear equations. You all know and love them. Something like 4x minus 5 equals 3. That's an example of a linear equation. Would you have a problem solving that equation? How would you do that? Right, at 5. Right, so divide both sides by 4. So x equals 2. Right? Done. Now, what does it mean to solve an equation, first?
Find out what the variable is.
So you want to find the value for the variable so that if you plug it in, the equation becomes an identity, meaning the left side identically equals the right side. So if I take 2 and I substitute it for x, 4 times 2 is 8, 8 minus 5 is 3, 3 equals 3, right? So, and we always want to find all values of the variable that make that work. So we'll see equations that have 2, 3, 5 different solutions that both work. But now with the linear. With linear, you either get one solution like that, you can get no solutions, or you can get infinitely many solutions. So there are only 3 options. Now, the reason why we call these equations linear, because really this is, if I try to graph the equation for x minus 5, that's a straight line, right? It's a line, slope is 4, intercept is negative 5. Because look, if I graph this, here is negative 5, up 4 over 1, very steep line, right? 4x minus 5. The other side is a constant, y equals 3. So that's a horizontal line. Let's say if this is 3, this would be the graph of that line. So what we just did, we found the point where they intersect. So this would actually be 2 here. That's what we found. We found the point where 2 lines meet. Okay? So 2 lines most likely will intersect at one point. If the lines are parallel, then they'll never intersect, so you get no solutions. Or you might get one line overlaps the other line perfectly, so they meet at infinitely many points. Did you know that? Good. Well, here's an example. 2 times 4 minus 3x plus 7 equals x plus, how about 2x plus 3 times x. I don't know what I'm doing. I'm going to go back. Trying to build an equation that's rather fun. So here's an equation. That's a linear equation. The key to the equation being linear is that the variable is x and there are no exponents on x, and there's no x's in the denominator. So how would you solve this equation? Right. Open up all the parentheses, combine like terms, and then go from there. So 8 minus 6x plus 7 equals 33 minus 6x plus 1. Right? So if we combine like terms on each side, 8 plus 7 is 15 minus 6x. On the other side, 33 plus 1 is 34 minus 6x. Okay? If I stop right here and actually think about what I see two linear expressions, right? If I think about them from a point of view of graphing, they both have the same slope, -6, but different y-intercepts, right? Now, we know that if lines have the same slope, they're parallel. So you're going to have two parallel lines. One crosses the y-axis at 15, one crosses the y-axis at 34. They'll never intersect. So this will have no solutions. But if I keep going solving this, because technically I need to get variables on one side, so I'll go ahead and add 6x to both sides. So it cancels over here and it cancels over there, and now I'm ending up with a statement 15 equals 34. Right? Can I make that statement into an identity? Can I make 15 equal 34? No, right? So that basically tells me there's no solution. Regardless of what x is, this will never work. So that's not true, so no solutions. Or graphically speaking, these are the two lines that are parallel and do not intersect. Right? Okay. Good. But in general, if you have an equation like that, open up parentheses first and then start grouping variables on one side, constants on the other side. All right, here's another example. So the only way I can make these equations challenging if I start doing something with fractions. So, well, that's a linear equation, right? How would we go about solving something like that? Multiplying what? Yeah, I really don't like the whole denominator thing. Every time you see that, you want to get rid of them. So how would you do that? By what? Yeah, but that's illegal. I cannot multiply one side by a number and the other side by a different number. So by 21. Okay, I like that. 21 is the least common denominator, so multiply both sides by 21. Because you cannot multiply one side by 7, the other one side. Don't write this down yet. One side by 7 and the other side by 3, because what you do on one side, you do on the other side. But if you have an equation of this form, where it's just a fraction equals a fraction, the easiest thing to do is to cross multiply that thing. This is the easiest thing that you can do, multiply them like that. Multiply the left numerator by the right denominator, and vice versa. Cross multiplication. Because again, don't write this part down, because you're absolutely right. I can go ahead and multiply both sides by 21, right? This would be legal. Multiplying both sides by LCD, but then 7 goes into 21 3 times, and 3 goes into 21 7 times. So I'm getting exactly the same statement, right? So it's just easier to just cross multiply in the case where it's just a fraction equals a fraction. If it's two fractions equals a fraction, it won't work. You have to go with the LCD. But if it's like that, just cross multiply, and then now it's simple. So distribute the 3, 9x minus 15 equals 14 plus 7x, right? And then add 15 to both sides, subtract 7x from both sides, we end up with 2x equals 29. So divide by 2. X equals 29 over 2, or 14 and a half. No, that would be the x value of the point where the two lines intersect. If I actually graph these two lines, let me show you. If I just type them in on a graphing calculator or whatever, which we don't need to do that, but it's good for us to visualize what's really going on. I'm going to use an online calculator. So what was the first line? 3x minus 5 over 7. What was that? 2 plus x over 3, like that? Yeah. So see that point where they meet? That point right there. See, it's right at 14 and a half or so. Okay, so if I actually put a trace on that point, so, I just have to be more precise. So here we go. 14 and a half on the x. So that's what we solved for. If I plug it in, and both functions will give me 5 and a half for the y value. But that's, graphically speaking, that's what we're looking at. We're looking at two lines, and we're just searching for the point where they intersect. Okay? All right, well, here's an example where we have more than one fraction. X over 2 minus 4x plus 1 over 3 equals x minus 7 over 6. So cross multiplication won't work here because I want to have fraction equals a fraction. Here I have two fractions on one side. But that LCD trick will work. If I ask you what is the least common denominator for all fractions here, 6. So just go ahead and multiply both sides by 6 to clear out all the denominators. So we've done that many times when we just distribute through the fractions. So we should be pretty good at this by now. When you multiply 6 by x over 2, 2 goes into 6 how many times? 3. So that becomes 3 times the numerator, so 3x. Now on the second product, 3 goes into 6 how many times? Twice. So that becomes minus 2 times the numerator. And on the right side, 6 cancels all together, x minus 7. So again, in one move, we no longer have any fractions. You can do this problem by messing with fractions. It's a lot harder. But now just open up all the parentheses, combine like terms, and solve. So if you combine like terms, we end up with negative 5x minus 2 equals x minus 7. Add 2 to both sides, subtract x from both sides, gives us negative 6x equals negative 5. And divide both sides by negative 6, x equals 5/6. So questions on this? Is that nice? You like that? So the bad news, of course, we're going to dive into equations that are not linear. But the good news is that the whole process of solving equations that are not linear is to turn them into linear equations. Everything that we're going to be doing is to, in the end, we're just going to be solving some linear equation, which is nice. But to get to the point of it being linear, that's everything that we learned this semester. We're going to use all those crazy little tricks and techniques and things like that. Okay? Good? All right. Well, I'm not going to teach you anything else today. Yes, go ahead. But I'm dividing, right? Because it's negative 5 times x. I'm sorry, it's negative 6 times x, so I'm dividing by negative 6. If this was negative 6 plus x, then I'll be adding 6 to both sides. So this worksheet is just full of linear equations. Okay? Oh, yeah, sure. Do you have questions on that? All right, so go ahead. What? What does that say? Okay. So this problem is going to be all about simplifying the radicals. So when I look at this first radical, the square root of 3x, there's nothing I can do about that, right? So most likely, the rest of those square roots will become square roots of 3x. That's what probably will happen in order for me to be able to combine like terms. Is that right? Because that's what's probably going to happen. The rest of those square roots will somehow become with a 3x under the radical. So when I look at 12x, how would I split 12x? So what? 3 and a 4. So it's 4 times 3x. Right? How about 0.003? Now remember what I said, there's probably going to be 3x left in order for this problem to make any sense. So what 3x times what equals 0.003? 100, yeah. So you can say it's 1 over 100 times 3x, yeah. That works. Now 1 over 100 is a perfect square. We'll be able to take the square root of it, right? Well, now, what is the square root of 4? So 2 comes out, and it gets multiplied with whatever's in front. And the square root of 1 over 100 is 1 over 10. So it also gets multiplied with whatever is in front. So 2 came out from the radical, and 1/10 came out from the radical. Is that okay? So 2 and a 2 cancel here, and 10 and a 10 cancel there. So we're down to 5 square roots of 3x plus square root of 3x minus square root of 3x. So not really, it's implied. Other questions? Well, 1h, we have a square root of mn times square root of m plus square root of n. So we'll just have to distribute, right? So it's a square root of mn times square root of m plus square root of mn times square root of n. Right? So what will happen here? Yeah. Yeah. That's fine, because you can pull them together to make it square root of m squared n plus square root of mn squared. Right? And then if you take the square roots, it's m square root of n plus n square root of m. That works. Technically, as we've discussed, the square root of m squared should be the absolute value of m, and the square root of n squared should be the absolute value of n, just to make sure those values come out positive. But in this case, it's not necessary, because since we started with the square roots of m and square root of n, m and n have to be positive to begin with. So m and n cannot be negative, so we can just ignore the absolute value. So absolute value gets really tricky. You really have to analyze what's going on. It won't hurt if you put the absolute value, but it will if you don't where you needed it, if that makes sense. Three E, the rationalizing. So 2 plus root 2 over 2 minus root 2. So what do I need to do in order to rationalize? What do I multiply by? Right, so conjugate of the denominator, right? So then in the numerator, I'm going to end up with 2 plus root 2 squared. While in the denominator, using the difference of squares formula, I'm ending up with that, 2 squared minus root 2 squared. Yeah? So now, so denominator is just 4 minus 2. That's simple. In the numerator, I'll have to use my formula, the square root of sum formula. So that's first squared, so that's 4, right? 2 squared, plus the double product. So if I multiply this 2, that's 2 square roots of 2, and then I double that. So that's 4 square roots of 2, plus the square root of 2 squared, which is 2 plus 2. Just using the formula. So that's 6 plus 4 square roots of 2 over 2. 2 divides both, becomes 3 plus 2 square roots of 2. Okay? Did you look at the example? Did the example make sense? No? No, it's not random at all. I've noticed that you guys have no idea how to factor, which is very sad. How would you factor 2 plus 2a? Take out 2, and what's left? 1, right? You need that 1 there. right? So when you had, in that example, you had root 2 plus root 6. Okay, so that's a silly example, but example went to tell you that this is the same, 6 is the same as 2 times 3, right? And by the properties of the square roots, that's square root of 2 plus square root of 2 times square root of 3, right? So what is the common factor? Root 2. So if I take the root 2 out, what's left? 1 plus root 3, right? Not random. That was the example leading to question 6. Well, but do you still need me to do anything on 6? A? Okay, well, A is root 15 plus root 10, right? So what you can do here, just if you think about, can you express 15 as a product of two numbers? 5 and 3. How about 10? 5 and 2. So this becomes root 3 times root 5 plus root 2 times root 5. So what's the common factor? Root 5. So if you take root 5 out, what's left? Yeah, so if you take root 5 out of here, that's root 5 plus root 2. Just factoring, just taking out the common factor. Yeah. This is just fun little exercises. So, but like on question 7, if I take a look, because question 7 is asking you to rationalize using some of those techniques. I mean, we know how to rationalize this. Multiply by root 3 plus root 6 over root 3 plus root 6. But here I'm asking you kind of do that same factoring trick. Because I can take out the root 3, right? Because what's going on here is that we have root 3 minus root 2 times root 3. That's the square root of 6. So if I factor out square root of 3, so it's 1 minus square root of 2 over square root of 3 times what? 1 minus square root of 2. Yeah? So what do you notice? Yeah, you can cancel the entire 1 minus square root of 2, leaves you with 1 over square root of 3. You still have to rationalize that, but that's a whole lot easier. You just multiply it by root 3 over root 3, so it's root 3 over 3. It doesn't work every time. I mean, it has to factor perfectly. But it just works in these examples, which is fun. Is that okay? Any other questions on this? Okay, so 5a is using whatever we did on 4. Okay, so 4 teaches you how you can factor using the difference of squares formula and square roots. Well, how would you factor that numerator if you can use square roots? And based on what you did in question 4, if you did that one. So basically 9 is what squared? 3. X is what squared? Square root of x squared. So I can actually do this. I can make it square root of x minus 3, square root of x plus 3. Because that works, right? So then I can just cancel the square root of x plus 3 altogether, and we're down to square root of x minus 3. Because with square roots, basically anything can be treated as difference of squares. If it has a minus in between, I can just always throw a square root. Right, I can say that x minus 10 equals square root of x minus square root of 10, square root of x plus square root of 10, if you allow that. Right, that works. Because of that difference of squares formula. Well, anyway, so start on your new worksheet and finish the old worksheet.
We have the whole worksheet.
Yeah.